All right, so we're going to continue where we left off last week on Monday. Remember, we're looking at this idea that we can use the first and second derivative to help us describe functions. Stepping into this idea of minimum and maximum values is definitely going to be an important thing that we kind of want to make sure we use as we're working with these. So the first derivative and second derivative help us with that. Now, there's a big difference so that you always want to watch for is, do I have something that we're looking at from an open interval perspective, or did they give me a closed domain to look over? Okay. So for this particular function, let's just look at the whole function itself. So as far as that's concerned, our first thoughts are, hey, we're probably going to be just relative minim maximums. Okay. But whenever we have a closed domain, so like if I said to use this to where X is just in this interval, the second you put a closed domain, you're going to have an absolute value, absolute minimum value, and an absolute maximum value. Okay, somewhere on that domain. Okay. Now, this function itself is different because it's rational. Okay. It's one of the things I want to make sure we've kind of talked about them, but I wanted to spend a little bit more time with it today. But anytime we're working with rational functions, what should we make sure we look at first? Make sure you're always watching your denominator. Make sure you see here, I put it in a factored form already. So the key here would be like, hey, a restricted value that I have to watch for is that X minus 3 can't be 0. So I cannot use 3. So make sure you remember to watch that. This is definitely something that we need to keep in mind as we move it forward as far as describing the function from different perspectives, especially considering the fact that that's going to have a big impact on the behavior. All right. So as far as the first derivative or second derivative, these may not be critical values, but it is something we need to consider. Okay. Now there's other things that you can do as well here if you wanted to, as far as finding, x-intercepts and y-intercepts. That's not what is required of us right now. So let's jump into the derivative aspect. So one of the reasons I wanted to make sure to look at rationals, and if we have time, I'll try to do two, is that don't forget the rules for derivatives, right? So as far as dealing with this to get to our function here, don't forget that anytime you have a rational function, you can use the quotient rule. It's gonna be low times the derivative of the high. We'll just say low d high minus high d low all over low squared. Okay. Now this one's not too bad though, because what's the derivative of x squared? All right, so if we just kind of make a note to the side, we can just be like, hey, I know the derivative of x squared is 2x, and the derivative, excuse me, of this x minus 3 squared is just going to be 2 times x minus 3. Okay. Since it's just x inside the parentheses, the chain rule would only give us 1 there. So we just make sure to need to put it in the proper order. So we'll do low times the derivative of the numerator minus high times the derivative of the denominator all over that low squared. And since I already had an exponent, we just double it. I will say this though, as we finish writing this one down, simplifying these definitely can be a little bit more tedious, but the reason we definitely need to simplify this is because we need to find critical points. So setting something equal to 0 is definitely going to happen. So we want it to have in a simplified form. What do y'all notice though about these two terms? They have stuff in common, right? So you can go do the multiplication, but always watch for that whenever you're dealing with the rational function, specifically this one here, right? that x minus 3 is the same as what's in my denominator, so we definitely want to pull that out. If you pull out the x with it, awesome, no big deal. But definitely make sure you recognize that that x minus 3 can be pulled out. Now you'll see here that I like the fact that we could pull out a 2x with the x minus 3. So what you'll see here is, as I highlight, they both have an x minus 3. They both had one x in common, but they also both had a 2. The reason I like to do that is once you pull that out, what's left over is pretty nice to work with. Right. Now, does it make sense that we have a -3 here? I'm tripping. A negative value, though, should be here, right? Is what I'm trying to say. We had something squared in the denominator, is what I'm trying to go at. Remember, you could also use the product rule. That's something I've shown in the past here where you use negative exponents. So if you rather work with the product rule, definitely remember you can do that as well. Cleaning this up just a little bit more. That'll give us what? -6x all over x minus 3 cubed. I should put the negative out front though. But make sure you see the reason I'm able to do that is I had one here, so I can just take away one from the x minus 3s. And then I just did this. These go to 0, right? So -3 times 2. Now, keep in mind though, if you do choose to use the product rule here, you'll get two separate terms that you would have to then find a way to bring together to get to this result. Are there any concerns though with getting to the derivative? Quotient rule isn't one that we've done a lot, so. But going forward then, we got a derivative equals -6x all over x minus 3 cubed. See if it'll let me. Now, once we get here, the next step is to find our critical points, right? Now, one thing that we do want to make sure we keep in mind is we have that the fact that x can't be 3, that still is going to continue with us. So as I go into looking at the first derivative and using it to help myself, that 3 is important. Okay. Now, as far as setting things equal to 0, once you get to the derivative, we're mostly interested in when the derivative is 0 or when it's undefined. Okay. Well, this is the undefined situation. That would give me the derivative equal to some number over 0. So I have that already by having stated it to start the problem. Okay. So as far as the other piece, just remember to set the numerator equal to 0. Okay. So the critical points that we definitely want to look at here are going to be x equal to 0 and 3. Now, as far as the function is concerned, we should expect 3 to be a asymptote. Because even after the derivative, it was still in the denominator. So it's probably going to be an asymptote. It's going to be more about what's going on either side of it. Remember, previously we did limits. I said, hey, what is the limit as this function approaches the 3 from left or right? But hopefully we'll see here that doing the derivative will help us with that. Now, the next step here is to get the increasing and decreasing of our function with this information. So we'll draw a number line. And on our number line, we're going to put the 0 and the 3. And at this point, what we're interested in is just plugging in some values around this to see what's going on. Um, just remember, like if we plug in 0, that's going to be the 0 and the, sorry, if we plug in 0, it'll give us a 0 or a horizontal tangent. If we plug in 3, that's where like, hey, I can't do it because it's going to be a vertical asymptote. Okay. What we want to do here is pick values around this. So what are some numbers y'all would like to plug in? I like those values. Well, if I plug in, say 7, does it matter what number I use over there? No, just as long as it's bigger than 3, right? Always try to use 0 and 1s though, if you can. Just make it easy on yourself. But also remember here, this goes back to like, okay, which function should I be plugging into? Okay. So make sure you see here, hey, I'm plugging into the first derivative I just found. So I want to make sure that I take these numbers that I'm saying and plug them in for X here. Okay. I think overall, most people were fine as far as going back to the correct function on the test. There was a couple parts. So like one of them, I like the problem because of if you weren't careful with your reading side of things, right? You used the function you found, but it really wanted you to use the function you started with, right? So always pay attention to what's going on. So like this one here, hey, we found the derivative, use the derivative. So let's go ahead and use it. Now, when I do this here, I get -3/32, or you might get a decimal. Doesn't matter about the number itself that we get back though. Make sure you see here what we're interested in is the fact that it's negative. The whole focus there is, hey, it's negative, right? What if we plug in 1? If I look at it correctly, it's going to give us what, 6/8? So if we plug in 1 here, it's positive. Definitely didn't have to use 7. I just picked something. Okay. That would allow us then to kind of start describing our function with what's taking place here. Now be careful how you interpret stuff here. A better way to have written the 3 here, I guess, would have been to continue with my red, huh? To say, hey, like, yeah, I use 3, but 3 is not going to be a relative or min or max for this problem. It's a critical point in the fact that it has some changing going on. On one side of our asymptote, it's going to be increasing, but on the other side, it's going to be decreasing. Okay. Now, with that said, the 0 is definitely a critical point that we found a horizontal tangent at. So what can we say is taking place at x equal to 0 for our original function now? It's decreasing, then it starts to increase, right? So there's a horizontal tangent here. We would call that a relative what? Minimum, right? So make sure you see there that, hey, that decrease, increase, I have a relative min going on. Now, as far as just kind of thinking about the graph here, though, what I would recommend is just kind of visualizing it. You don't have to have a perfect perspective here, just kind of a quick visualization. Our graph, all right. We have this vertical asymptote here that we're looking at for +3, right? Now, the other thing I would say here is make sure you understand that as we looked at these, what I really should be pointing out is whenever we're working with rational functions, remember we have an end behavior we can look at as well. This is where we talked about the limit as x goes to infinity, positive or negative of our function, right? We were saying, hey, what happens on the very ends of that function? The one thing I will say is if you go to your original function, remember some of the stuff that we talked about in college algebra, the degrees are the same. It's just a ratio of the leading coefficients. So you'll see here, since this is x squared and this would give us x squared, we could just do the quick division. Well, x over x is going to give us 1. Okay. So based on that, we know we have both of those approaching 1. So we have a horizontal asymptote as well. I know I went in a little bit more detail about that the other day, but just remember identifying a horizontal asymptote or what the end behavior is doing is going to be an important part of rationals. What you'll see here though is this piece is what we got to focus on. Okay. Over here, we know our function is decreasing, but that's not what rational functions do here. So this is where we have to remember how rational functions behave. Okay. And what we'll find here is the rational function is actually going to do something like this. This is definitely a little bit different because of the fact that typically we don't cross asymptotes, right? But the vertical asymptote is the one we don't want to cross at all. Horizontal asymptote just affects end behavior. Okay, so like if we want to go do a quick sketch of this, we know that this is going to look something like this here. Where my function will look horizontal dip down, start increasing. And then over here, it's going to look something like this. Not a perfect graph. I could clean this piece up here because remember, this is going to be a relative min. So I didn't draw it perfectly here, but the idea is that point is a relative min. But the nice thing about that is we know that it's increasing on one side, decreasing on the other side. So we have the behavior around that asymptote given to us as well based on what we have here. Okay. Now, just as far as like getting to the graph that I just drew, just know plugging in points is what I definitely recommend at that perspective. The one thing I want you to see here is don't forget about your limits. Okay, that's where I got this horizontal line from. The nice thing about rational functions, if you take the stuff we learned in college algebra, just look at your exponents. Those are both polynomials, right? So since they're the same, I just said, hey, that's a coefficient of 1, that's a coefficient of 1. So that's where I got this 1 from. Okay. What we call horizontal asymptote. Not everything has a horizontal asymptote though, so just be watchful. This piece here though is the one that we're starting to see, okay, hey, the reason it does this is because I still have a critical point with the first derivative that's not the asymptote for the vertical one. Okay. So our function is going to be, it's going to look like it's horizontal, dip down, hit that point, and then turn up. Okay. Is there anything I'd help with as far as interpreting that first derivative? Don't forget to use your interval notation, of course, here. So we'll see it's decreasing from negative infinity to 0 and 3 to infinity. And then it's increasing from 0 to 3. Is there anything I clear up for somebody? Now, the piece here then I would continue with is let's go look at the second derivative to see if it confirms what we found. Okay. As far as the second derivative is concerned, make sure you see here, that's always concave up. Okay, so when we go look at this here, we should see a positive value with our second derivative. So there's going to be some changes that take place. But also see that as we look at this piece here, there's going to be some complexities that we need to look at because there's a change that takes place there. Okay, so let's go look at the second derivative now. Now, as far as that's concerned, again, we have to do that the low d high minus high d low all over low squared. So we'll do the derivative of the 6x, the derivative, oops, of the x minus 3 cubed. And then we'll fill it in. And remember the denominator, we're squaring it, right? So I'll just double that from a 3 to a 6. Now also be careful. I almost forgot my negative symbol there, so don't get your negative all the way on the front. One thing I would point out though with this again is that, hey, look, the numerator has that same kind of pattern as far as simplifying is going to take place. These both have x minus 3 in them, right? So I'm going to bring 2 of those out to help with the simplifying aspect. I'm also going to pull out a 6 with it as well since I have those here. Make sure I'm not messing something up here. Is that what y'all get? Now, the first one was nice because the 2 terms canceled out, right? With this one here, we have to be watchful how we handle it. Make sure you see here. Well, what, negative 4x minus 3? Hmm. Yes, negative 2x. Sorry. Thank you. X minus 3 to the 4th. And then I would distribute a negative 6 through there. You don't have to distribute the 6 at all. The main thing I would do is distribute the negative, though. Okay. I'll leave the 6 out just to show you why, but make sure you distribute that negative. Now, if you're trying to keep track of what's happening here, make sure you see the original denominator was squared, then it went to cubed, and now it's to the 4th, right? So kind of a similar expectation when dealing with rationals there. From the power rule perspective, right? The denominator, if it's in the denominator, it's a negative exponent. So it's going to be decreasing, which is, we're seeing the increasing take place there because it's a negative exponent. Now, make sure you see here, I had that negative out front, so I almost forgot. So that's where that change is coming from. Now, as far as dealing with this, we're trying to find points of inflection now. Okay. So when we look at the points that are important for the second derivative, make sure you see here, when I set the second derivative equal to 0, that's just going to be that factor there. Which if you distribute the 6 through, no big deal. But if you leave the 6 out, it's a little bit nicer form to be like, hey, that's just negative 3/2. Right. The nut 3 and 2 don't work together as far as division. So just change your sign. Okay. Now, keep in mind though, at the same instance, don't forget that you cannot use 3. That would be the other thing that we need to watch for. Now, make sure you're also looking at this. This is the second derivative. So this is us looking at the concavity of a function. So like when we look at this here, we're thinking concave down or concave up. Those are the kind of overall thoughts that we're going through our head. And that would always, that's one thing, if you ever forget, just remember like, hey, this is negative x squared, that's positive x squared. Do 2 derivatives on that simple function to see like here, if you do 2 derivatives, you'll get just -2, where over here it'd be a +2, right? So to kind of see where that's coming from, okay? Everyone good with though getting to the second derivative and where that -3/2 is coming from? All right, so with that said, let's bring the second derivative over with us and look at the concavity of this function. Now, the one thing that hopefully you saw in my first derivative, making sure to state what you're focusing on is going to be important here. So now we're plugging into the second derivative, okay? So we want to make sure to make that distinction. As far as plugging in values here, I would use -2, 0, and 4. I pick -2 because it's the closest I can get to 3/2. 0 is always nice to work with, and then 4 is just one more than 3. Going through and plugging these in though, this is going to give me a negative value when I plug in -2. Specifically, I got -6/625. Not necessarily the nicest number to look at, but the key is it's negative when I plug it in. If I go plug in now 0, that should give us what? 18/81, 2/9. Again, it's positive. And lastly, plugging in the 4, as I mentioned, this one we kind of looked at, we should expect this to be positive, and I get a 66 when I plug in the 4. So you see it's concave up there. Now, as far as this is concerned, this is us looking at our asymptote, right? So that's kind of confirming the fact that we should expect around our vertical asymptote, our function is going to look something like this. Okay. Now, the big difference here is, as we looked at, this piece is going to go towards our horizontal asymptote here, right? This piece, however, has a little bit of a change taking place. It's a little bit different. All right, as we've looked at, hey, this is going to dip below that asymptote a little bit. And then we have this change taking place where one side it's concave up, but the other side I need to draw concave down, right? So what do we call this value here because of that change that takes place? Right, that's our point of inflection. And what you'll see is you'll go over here like, hey, this is where x equal to 0 is at. That was our relative min that we had. Well, if we go over here a little bit, the idea is that, hey, when I have a point of inflection, one side I'm going to draw kind of like this U shape over here like that. But on the other side, I'm going to use an upside down U shape. So from there, I could draw that out as such. Okay, now this one's a little weird because it's kind of hard to tell that that takes place at that specific point because, you know, those values can all be pretty close to one, right? With that in place, though, just make sure you see that, like, hey, there's a change that takes place here where this is considered concave down. A little bit nicer with the polynomials, you could see the exaggeration of these a little bit more smooth. Like if you're dealing with something that's cubed, concave down, concave up, somewhere in between then there was an inflection point. The one thing I would say here, though, if we want to get a graph that's as accurate as possible, I would use these points that I found, go start plugging things into that original function, right, to get better points. So like one of the things that we could go find would be that x-intercept possibly. Okay, we would definitely want to consider that. But if I remember right, this was the x-intercept, right? If we go back to our original function, yeah, that's our x-intercept. So we're going to drop down, touch that x-intercept, and then work our way back up. Okay. Now, as far as dealing with these areas of concavity, know that whenever something is concave negative, the only thing you can have on that interval is a relative max. When it's concave up for being positive, the only thing you could have on that interval is a relative min. Okay, so if we can have a relative min from -3/2 to 3, does that disagree with what we found? That's the very thing that we said that 0 was, right? Was a relative, oops, too far. We did all that work to show that there was a relative min here, right? It drops down and then back up. So that confirms what we found earlier. But the second derivative helps us with that. Like as we're dealing with this, going back and saying, hey, these are the places where I can have relative extrema at. That's where it's possible. Okay. What we find here is I can have at most 2 relative mins and 1 relative max. This particular function, all we had was the relative min, though. That doesn't mean you have an extrema on that interval, but you can have one. Any questions or concerns with that? Yeah. Which I remember I picked on this one here because we knew that there was a relative min there, right? We did the work that, yeah, that definitely confirms that 0 can be a relative min. Okay. What we found is if I go look at this graph, I could have a relative min here, but based on how rationals work, not this time. Okay. Over here, I could have a relative max, but again, that asymptote, that what we call horizontal asymptote kind of affects that where we didn't even have one. Okay. Does that help? Any other questions or concerns? Now, what did this help us with that is a little bit nicer? Well, hopefully you saw getting to this behavior, you didn't have to do a limit. Right? If you know something's, you know, increasing and concave up, hey, I need to approach it as such. We can then go answer our limit based on that quick sketch or understanding of what the derivative tells me, right? That, hey, as I go from the limit of either side of 3, whether it's left or right, they're both going to approach positive infinity. Okay, so it allows you to better describe a function and, you know, connect the limits to what we're doing. Okay. Excuse me. All right, so here's another one that it's a little bit more involved as far as the work is concerned. I want to go through this though, just to make sure we practice the quotient rule again. But also just reminders that, hey, just be prepared to have to deal with functions in different ways. That's going to be the tough part here, right? As we deal with functions and dive into them, different things can happen. Now, one thing I would point out with this function here, what in the world did I just do? What happens when you try to find a restriction? All right, so be careful with that, right? Because when you do that subtraction, it's not positive four, it's now negative four, right? Which, hey, the square root of four is two, but what should we put with it? 2i, right? So do I have restrictions? Right, so make sure you see here, no restrictions. Does this have a vertical asymptote then? No, right? We're not working with complex numbers, right? I'm sure there's some areas where you can connect complex numbers to different business models. But for the most part, we're going to be working with real numbers, and more specifically, as we see with a lot of application, positive real numbers. Okay. So here we'd be like, hey, I'm not even worried about restrictions. I just need to now move into finding the derivative. And once I find the derivative, my critical point is going to come from the numerator. That's it. The denominator doesn't have the same impact on this, but just make sure you're watchful for this to occur. It's not going to happen all the time, but just remember, hey, no restriction, I can move forward. My domain for this is all real numbers. Now, as far as dealing with this derivative, just make sure you go back to the fact that we're doing that low times the derivative of high. So low d high minus high d low all over low squared. So to help start that, I'm going to do the derivative of those separately. Now, I will say this one's not as nice as the previous one. I get that. But just make sure you're careful putting everything where it goes. So like we're starting with low times the derivative of the top. Minus the top times the derivative of the denominator. All over that p squared. The one thing I would contrast here with this one is like that greatest common factor situation that we had before does not work out as nicely here. You could find ways to pull it like a two. But if it's not going to involve an X or a whole factor, that's up to you how you want to handle it at that point. I'm going to leave the twos where they're at and just work through. Okay. Now, the one thing I will not multiply out is the denominator. Don't worry about multiplying that out. Should be squares, not to the fourth. Because like if you need, like when we go talk about the second derivative of this one, having it in that form is going to help us. I'm not going to have time to do the second derivative with this one because as you can see, it's going to be a little bit more tedious than even this one is as far as just the simplifying aspect. Okay. But what I want to make sure to point out is how do we handle this, the first part as far as dealing with critical points. Make sure that should be, yeah, that's what I say something's wrong. So the nice thing about that is once we fix that, those drop out, right? If you have the fourth down, I apologize. It shouldn't have been 4. So that will give us negative 18x squared plus 16x plus 72 all over x squared plus 4 squared. Any concerns where we're getting that from? I could help someone with? Not as bad as it seemed because those two terms dropped out, but that wasn't guaranteed to happen. That was just because of how I chose to build the problem, right? Now, once I get here, we've already set the denominator equal to 0 and found that it gives me complex solutions, right? So all I need to deal with here is say, hey, I'm trying to find critical points where horizontal tangents occur. That's our whole focus, right? The denominator is still x squared plus 4. It just happens to be 2 of them now rather than 1 of them. So I don't need to worry about that. Just make sure you see here, this is where the fun of quadratics can get mixed into problems. Okay. The one thing I would point out here with this one is make sure you see all those things are even. You could help yourself out by going through and recognizing, hey, I can divide all of these by -2, and that'll help make something like the quadratic formula just a little bit nicer to work with. If you want to try to factor it, even that would make the factoring nicer to work with, because now we'll have 9x squared minus 8x minus 36 equal to 0 rather than having that 2 mixed into it. And just a quick glance, I really don't think this is factorable, right? Which is why I picked it. Because this is where we have to go back in our skills and knowledge from college algebra, right? If I can't factor it, we can either complete the square or use the quadratic formula. Which means I would expect you to use the quadratic formula with this one. Everyone follow me on that? Is everyone good with the quadratic formula? All right, so remember that there's our C value, and that's my A value. I kind of squeezed it in. So it's 4 times 9 times negative 36. That's going to be 64 plus 1296, which will give us 1360 down here. You could definitely jump in there and start trying to simplify that radical. But what I would say here is just always pay attention what the problem wants from you. It's like when I think about this one here, I think we can pull out a 4 at least. Looks like you pull 16 out of it. So if you want to go through the simplifying process, just make sure you see that this square root of 1360 can be written as 4 square roots of 85. The idea is 85 times 16 gives you that value. Not something I would expect you to know off the top of your head. I knew what 4 goes into because if you look at the last 2 digits of a number, if those 2 digits are divisible by 4, then the whole number is divisible by 4. So hey, 4 goes into 60, I can divide 4 into this. Okay. Now, with that said, that won't necessarily help us at all, except for to show that, like, hey, I can simplify this a little bit by writing it as such. But even then, it does not help us in getting to nicer values. Okay, so whether you leave it in this form or you go through the whole simplifying process, just know, like the homework, the Pearson side of things, they'll show the second one here. I pull this out from here. But just make sure you see 18 and then that 4 all even, so I can divide everything by 2. Okay. But where can we put this to get approximations? Put it in the calculator, right? Understand, as far as approximations are concerned, the nice thing about it is we could still jump to a number line and use those approximations to help us with that. So if I go do it real quick, just we're gonna have 2.49 for the plus sign. Negative 1.60 for the negatives. Don't pick anything, right next to it, but you could safely say, hey, I could go do that whole thing we just did before, but I'm just gonna use 0. I'm gonna use 4, and I'm gonna use -2. I'm gonna try to stay away from them as much as I can. I think you'd be fine with using +3 if you wanted to. Okay. But you'll see this is where just making sure we watch for different skills that we don't necessarily use there. We haven't used the quadratic formula all the time. Okay. It's like the synthetic division problem we did the other day. You're not going to have to use synthetic division all the time, but don't forget that sometimes you will need it. Right. Here's an example of, hey, we may not have to use the quadratic formula all the time right now. But to be honest with you, once you get out of this class and you start using this with a real world application of it, the functions will not be nice to where you can factor them all the time. You're going to probably have stuff that's dealing with decimals as far as the coefficients are concerned, because the statistics will form a model that fits even better than what we're using here. Okay, we're just picking models that, hey, yeah, we're doing exponentials, polynomials. So the general idea is good, but we're just trying to make sure we understand the process. When we step out, quadratic formula is probably going to be used more than anything. Okay, does that make sense? Any concerns or questions with that? Now, we would need to go further with this, but we're out of time today. Just know though, my focus on this one is don't forget the quadratic form. Okay. The first one covered everything to expect here. This one you'll find, I don't remember off the top of my head, but it'll probably look something like either this or the reflection of that. Okay. These are matching degrees. So we still have a horizontal asymptote there. So that's where you're going to see it should look like one of those two. If you go further with it, okay? Any questions, concerns as y'all packing up and now? All right.